Hi there. In this video, we're going to talk about polar coordinates. So let's start by reminding ourselves how Cartesian coordinates work. Cartesian coordinates are the ones I think we're most familiar with. In Cartesian coordinates, we have a pair of axes. We have an x-axis and we have a y-axis. And we use these axes to describe the position of any point in two-dimensional space, in the two-dimensional plane here. So if I take a point, the way I describe its position is by measuring the displacement away from the origin, where the two axes meet, in the x direction. And so I go about that far. Let's call that x. And the displacement in the y direction, let's call that y. And then I can label my point with coordinates x comma y. So I know that when I give numbers x and y here, surrounded by parentheses, I know I'm talking about the first number representing the distance or the displacement in the x direction, and the second number talking about the displacement in the y direction. And that's how Cartesian coordinates work. Well, we can also do things a different way. We can do things as follows. We're still going to draw an x and a y axis. So this is still the x axis. And this is still the y axis. But to describe the position of a point, what we're going to do is we're going to talk first about the distance that that point is away from the origin. And then secondly, we're going to talk about the angle that this ray that I just drew here makes with the positive x-axis, where that angle is measured in the counterclockwise direction. And we'll call that angle theta. Now, if I think about that, the distance that a point is from the origin and the angle from the positive x-axis, I can use that to describe the position of any point in space. So these are valid coordinates that I could use. And so I could label my point r theta. And these are called polar coordinates. So we're still using just a pair of numbers, but those numbers are interpreted in a very different way. All right, I just want to take a moment to show you the difference between how we locate a point using these two different coordinate systems. So suppose we're talking about the point 1, 2. All right. Now, in Cartesian coordinates, what does that mean? Well, that means my displacement in the x direction is 1, and in the y direction is 2. All right, so that is the point 1, 2 right over here in Cartesian coordinates. Now, what if I was working in polar coordinates and someone gave me this point? Well, the 1 tells me that it is distance 1 from the origin. Right? So I know I'm going to be exactly 1 unit away from the center. The 2 is the angle measured from the x-axis. We always assume that angle is measured in radians unless specified otherwise. Now, what is 2 radians? Well, we know that pi radians gets me halfway around, right? So it gets me to the negative x-axis. And pi is about 3.14, right? Well, 2 is about 2/3 of that, right? So I know that my angle is going to be get me 2/3 of the way over there. And my distance from the x-axis is 1 unit. So I'm actually right here. So in polar coordinates, the point 1, 2 would be over here. Notice they are very different. So we really need to understand what coordinate system we're working with to understand what a point given in coordinates actually represents. One other important thing that we might want to do is convert from one coordinate system to another. So suppose I know my coordinates in polar form, and I want to know what are the coordinates of this point in the Cartesian form. Well, how would I do that? How would I figure that out? Well, I know that in Cartesian coordinates, I'm looking for the displacement in the x and the displacement in the y directions. So I will just draw this right triangle over here, and I'm looking for this displacement in this direction and this displacement in that direction. How can we figure that out? Well, we can use a little bit of trig, right? We know from trigonometry that the displacement in the x direction is just r cosine theta. So to get the x coordinate over here, we know that x is equal to r cosine theta, and the y is r sine theta. That follows from trigonometry. So that's how we convert from polar to Cartesian. Now, what if we want to do the other way around? What if we know our coordinates in the Cartesian coordinate system, and we want to write them down in the polar coordinate system? Well, what we need to do is we need to figure out this distance here, that's our r, and we need to figure out this angle, that's our theta. Well, what do we know here? Well, we can draw that right triangle again. Well, we have the Pythagorean theorem. The Pythagorean theorem tells us that the length of the hypotenuse of this triangle, which is just r, if I square it, it is just x squared plus y squared, right? So that's a formula for r. I also know from trigonometry that the tangent of this angle is y over x. So I know that tangent of theta is equal to y over x. So this is a set of equations that I can use to determine r and theta. And this is how we convert in this direction, going from Cartesian to polar. All right, so next I want to take a moment to just look at some equations and see what they look like in polar form. Let's remind ourselves of some basic equations in Cartesian form. If I look at the equation y equals 1/2, all right, there we go. So it is the line, it is a horizontal line consisting of all the points whose y-coordinate is equal to 1/2. So we see that it's just this straight line here. And if I look at something like x equals, let's do something a little bit different. Let's do 3/2. How about that? I see what I'm getting here is I'm getting all the points whose x-coordinate is 3/2. So it's this vertical line here, right? And of course we can look at other equations like y equals 3/2x, right? We get a line with slope 3/2 going to the origin. Okay, so we're used to this. Like, we know this very well. Well, what if we start using polar coordinates? What if I say r equals let's say 3/2? Think about what we're going to get here. Let's work this out. Remember what polar coordinates specify? Well, r, what it specifies is the distance from the origin. So if I say r is equal to 3/2, I'm looking at all points whose distance from the origin is 3/2. So think about what that's going to make before I type it in here. And if you had guessed a circle, then you were right. It's the set of all points with distance 3/2 from the origin is just a circle. What if I specify theta equals something like, Desmos won't actually, the program I'm using here is Desmos. It won't actually let me specify equations in theta. It doesn't graph those well. So I'm going to use a different software. I'm going to use Maple. So let's see if I can do that here. So turn off Desmos. Okay, so I've got it set up. I'm going to plot theta equals 2. You can see I'm just setting theta equals 2. And I've got some other parameters to get it to look nice when I hit the plot button here. And so there's my plot. See if I can make that a little bigger. Now, what's that doing? Well, it's looking at all points that are angle theta equal 2 radians from the positive x-axis. So this angle here, right here, that's 2 radians. Similar to the point we plotted previously in an earlier example, right? But it's looking at all points whose angle is 2 radians. So we have r could be anything, right? We could be any distance. And in fact, it's also plotting for a negative r. You can see r can be negative and we're going in this direction. But angle 2 radians and r could be anything. We get a straight line at that angle. Okay, let's try something just slightly more complicated. Let's try r equals theta. See what that gives. What is this shape doing here? If we zoom out here, we see, oh, look at this. It's a spiral. Now, why is that? Well, when we start here at theta equals 0, r is 0. So that's why we're starting at the origin. And as I increase theta, well, r is equal to theta, so r grows. So as I wind around, I get farther and farther from the origin because r is equal to the angle that I've wound. So as the angle grows and grows and grows, r grows and grows and grows, and we get a spiral shape. Pretty neat, huh? So let's try r equals cosine theta. What will this make? Well, look at this. We get a circle. Okay, well, okay, maybe it's a simple shape. What if I put a 2 theta here? What do you think I'm going to get? Let's see. Cosine 2 theta. Well, this is pretty interesting. Look at this shape. You'd be hard-pressed to try to write a shape like this using Cartesian coordinates. This 4-petaled flower here. Now, let's see if we can reason out what's going on here. Well, when theta is 0, right, cosine is 1, so r is 1. So at angle 0, we are positioned right here, right, at this point. Now, as theta increases, we're going to be moving up this curve. But as theta increases, cosine gets smaller, so the radius is decreasing. So that's why this petal is coming in towards the origin. And by the time we get to theta equals pi over 4, then 2 theta is pi over 2, at which cosine becomes 0. And that is why when we get to about angle pi over 4 here, we come into the origin, right? Now when theta moves past pi over 4, cosine 2 theta becomes negative. So as we go up here, we're actually negative r, and so what we end up doing is we end up lapping around here and then coming down this loop over here. And then we come this way, and then we come up here, and then we go over here, and then we loop around, and then we spiral around up here, and then we come back to the origin. So that's how we trace out this flower shape. So you should be able to graph something like this on your own without the aid of graphing software. Takes a little bit of time, but if you reason it out like we just did, you should be able to figure this out. Now, what about cosine of 3 theta? Well, this is an interesting shape. What about 4 theta? What about 5 theta? So we're seeing a pattern here with the flower shapes here. Okay. What if we start doing fractions? What if I do theta over 2? What are we going to get? Well, this is interesting. This is an interesting shape. And again, we could reason this out. You should be able to graph this without the need of graphing software. When theta is 0, cosine is 1. So when theta is 0, radius is 1. That's why we're over here. Then theta starts to increase, and cosine theta over 2 will decrease, right? So it's going to come down. It's going to get closer to the origin. And here we are at theta equal pi over 2. When we go past pi over 2, as theta approaches pi, well, then theta over 2 is approaching pi over 2, and cosine of pi over 2 is 0. So that's why, as we come around here to theta equal pi, this curve is coming into the origin. And then when we move past pi, theta, r becomes negative, right? Because cosine of pi over 2 is negative. So then we loop up this way, and we come around this way, come around here, keep increasing theta. We'll eventually come back to this space, and then the process starts over again, right? So interesting shape there. What if I do theta? What if I do cosine theta over 3? And maybe not what you'd expect, right? But that's what it becomes. And if you reason it out, you can see why. What about theta over 4? Wow. You get some really interesting shapes. What about theta over 8? Some crazy stuff going on. So different, very interesting plots we're seeing here. Now I'm only plotting from 0 to pi to 12 pi. If I go from minus 12 pi to 12 pi, you can see it fills in some of those gaps we saw before. So But you can see that generally when we deal with things that have this circular nature to them, polar coordinates might be a better way to go about describing what they look like.